Okay, so this is a short demonstration of Pascal's principle. This is a boot. It's a rubber boot, and I'm going to fill it with water, and I want you to notice there's some holes on it. There's a hole here, and a hole here, and a hole here. And then there's holes on the bottom. There's a hole in the front, and there's a hole in the back somewhere. There you go. And as I fill this with water, you'll notice that water starts running out of the holes. There's some cloth on the inside, so sometimes it blocks them a little bit. But mostly what I want you to see is a couple things. First of all, the water will shoot out from the holes that are on the top, and so there's upward pressure on the surface on the inside, as well as pressure on the downward parts, right? So in other words, I want you to see that the pressure acts in all directions. Also, as it fills up with water, you're going to see the water come out faster. And you'll see a few things, like the water from this hole will come out slower than the water from this hole. You'll see more of a straight line coming out here and a little more curved because there's less water above here. And so that'll be an indication that the pressure varies with the depth. So let me turn this on. So all I'm doing is I'm filling this up with water, and right away you can see water coming out of the bottom maybe. Right, and as I go, you can see water kind of coming out of the different holes. And notice that the front hole is getting more water than the toe in the hole. The water's coming out faster than the hole at the top, the hole in the toe. It's coming out of this one, it's coming out of that one, it's coming out of the back one, it's coming out of the bottom one. And the farther down they are, the faster the water goes. Okay, that's a little bit of Pascal's principle. So this is called Pascal's vases, and it's a similar concept. These are just little tubes of different shape, all connected together, and I'm going to fill it with water and show you that when I fill it, they all fill to the same height, even though they're all different shapes. So I'm just dribbling a little food coloring down these things so you'll be able to see the water when it gets in there. And I do my best to not overfill it. And so first I'm going to turn the water on, but just barely. And then I'm going to try to get some water in there. And so you can sort of start seeing it, I think. And so I've got to slosh it a little bit to get it to the same height. Right, but you can kind of see if I hold it steady that they're all at the same level, right? If I tip it one way, the level of the water stays the same. The variation of the pressure with depth is the same, and so if they're all atmospheric pressure at the top, because that's where the air is, right? And so the pressure will be the same going down as long as they're all at the same level. And so it doesn't matter what shape they have. All that matters is what the depth is. All right. Okay, so we're going to talk a little bit about Archimedes' principle. Archimedes' principle states that the buoyant force is equal to the weight of the displaced water. And so this is a 2-liter bottle, and I've cut a hole out of the top, well, out of the side, but it's going to be out of the top because it's like a boat. And so I'm going to hold it like this, and I'm going to lower it down into the water. And if you notice when I do it now, it floats with just a tiny bit submerged, right? The net vertical force on this plastic bottle has to be 0 because it's not moving other than bobbing a little bit, right? And so that means the gravitational force pulling down on it has to be balanced by the buoyant force pushing up. And so the boat sinks until an amount of water equal to its weight is pushed out of the way. That's what Archimedes' principle says. And so, since this is a 2-liter bottle, the density of water is a gram per cubic centimeter, or a gram per milliliter. That means 1,000 grams per liter, or a kilogram per liter. Or this bottle holds 2 kilograms of water. And so if I were to put 2 kilograms of weight into here, it would have to displace the whole volume of the bottle, the full 2 liters, to stay afloat. And so you'll see these are, I'll sort of read these off to you. This is a 100-gram weight, and so there's 100 grams, and 100 grams, and 100 grams, and 100 grams here. And you can kind of see that now the boat's sinking down a little bit into the water. It's definitely not halfway submerged yet, but it's getting down in there a little bit, right? And so that was, I have 400 grams in there. I have a couple of 200 ones. These are a 200 gram. These are the same weights we use in lab. And so if I drop those 2 in there, now there's 800 grams of mass in there, and you can see it's almost halfway sunk, the bottle is, right? If I add a couple of more 100s, it should look about halfway sunk. And that's what you see. The buoyant force is equal to the weight of the water that's displaced. I'm trying to balance it a little bit, right? And so if I have a kilogram of mass in this bottle, it's got to sink down so half of its mass is pushing water out of the way to get the buoyant force equal to its weight. And so you'll see as I'll add more mass to this. Here's another 100 grams. So we're at 1,100, 1,200, 1,300, 1,400, 1,500, 1,600, and already we're getting pretty low. Now you can probably see that the top of this thing is cut open, and so we're not going to be able to get all the way to 2,000 grams or 2 kilograms before it starts to sink. Here's 1,700, and already it's starting to run in a little bit. And there's 1,800, and that's it. And you can see it sink, right? And so that's a demonstration of Archimedes' principle, that the buoyant force is equal to the weight of the water that's displaced. In other words, as I add more weight to it, the boat has to sink further and further deeper into the water to displace more water to hold up the amount of weight I put in. So I can do a few more demonstrations of Archimedes' principle. One is, these are some very old pop bottles. This is a bottle of Coke, right? And you should see that when I put it in the water, Coke kind of sinks a little bit. If you look carefully, I don't know if you can see that, but there's air bubbles in the top. And so that's really what's holding it up. The bottle wants to sink a little bit under the surface. If I get it right up against this, you might be able to see that the air bubbles are below the surface of the water. And so the water in the pop is heavier than the water, more dense than the water that's in the tank. Whereas if you try Diet Coke, it floats a lot better. Right. Here are a few other bottles we have. Here is alcohol. You should have an A on top. See if you can guess what it's going to do. Alcohol floats well above the surface of the water. What about the salt water? This has an S on it, but you can't see it anymore. What does salt water do in regular water? Yeah, it sinks. And finally over here I have just water. And so water should be roughly neutrally buoyant in water, which it seems to be. And so you can try all kinds of different things. Has anyone played golf? What does a golf ball do? Yep, you don't get to hit them off the surface of the water, do you? Ping pong ball? Right, the ping pong ball sinks until it's displacing its weight in water. It doesn't have to sink very far because it's hollow, it has very little mass. And so it just has to push a tiny amount of water out of the way. So I have a cup here, and I'm going to weigh it. And hopefully you can see that that's around 2.8 newtons or something like that. Cup's just hanging, just like this. It's not in the water or anything. And it weighs 2.8 newtons. And so now I'm going to look at what the scale reads when it's submerged. And hopefully you can see that instead of 2.8 newtons, it's now 1.2 newtons. And the reason it weighs less is because it's submerged in water now, and there's a buoyant force pushing up on it. And it turns out we can use that information to determine the density of the material. Remember, density is mass over volume. And if you wanted to find the density of this cup, it would be challenging to measure its volume. And so this is a clever sort of technique for measuring the volume of materials by taking what a scale reads for them when they're submerged or not submerged in water, or really any liquid. So here's another example of Bernoulli's principle, and this is called a Venturi tube. And so this is a glass tube that's got sort of three forks coming out of it. They're all connected, and I attach them to these to this top tube. And as soon as I get this thing hooked up, I'll talk about it. So I want to dribble a little food coloring in there, so you'll be able to see the water once I get it in. And I'm going to take this, I'm going to dribble some water down in there. And now I'm going to try to slosh it back and forth so you can actually see it. Whoops. Okay, now I'm going to seal it up. All right, and so now I have three tubes that are about the same level, and I'm going to blow through this one. And so if you notice, the top tube is wider and then thinner and then wider again. And so where's the air going to be flowing the fastest? If I blow through this end of the tube, right, where's the air going to be blowing fastest through? Is it going to be here, here, or here? Hopefully you answer here. The tube's narrowest, and all the air has to go through it, so it has to go faster through the middle than it does through the edges. And when you look, you'll see that the middle column will rise the most. Hopefully you can see that on there. In areas where the air is moving the fastest, the pressure is the lowest, and so the water rises up to equalize the pressure further down the tube. And so because this has the lowest pressure above it, the water rises the most here. This gets a little lower than this side because this one has a little more back pressure on it. All right, that's a little bit about the Bernoulli principle, a little bit more about the